but this allows you to constantly be able to do predictions, even one data point at a time, okay? With the idea that this posterior will actually converge, and you can even say to yourself, I don't need more data, now I am good enough, thank you very much, okay? So this is a very nice feature of Bayesian analysis. One slide before I move to a more interesting topic. Yeah, so you remember we defined the posterior, we talked about point estimates of the posterior, we defined the predictive distribution, very important. We said nothing about the marginalization on the bottom of Bayes' rule. And you remember that involves the likelihood times the prior and integral in the parameter space. Okay? Now, if your objective is to calculate the posterior, okay, 95% of the times you don't really need to know this. So if, for example, if you're going to draw samples from the posterior, you don't need to actually normalize the posterior distribution. You don't really need this. If, however, your objective is to compare different models, okay, so to do, let's say, what's called model selection, then model selection will be based entirely on this marginal distribution of X. At the end of the day, right, you collect data X, and you want to basically figure out what is the model that gives you the highest probability, this marginal distribution of X. Because if you have two models to compare, who cares what parameters one model uses and who cares what parameters another model uses? The only thing you care is the probability of the data under this model higher than the probability of the data under another model. Okay, so if you want to compare models, that is based on this marginal distribution of X, and we will spend one lecture on this. All right, so we're going to come back because it's extremely important in a Bayesian setting. Okay, so we can now take a break. It's 4:22, and let's see what slide we're supposed to go. We're going to start a new topic, which actually will tell you that Bayesian analysis can get complicated, but also can be generalized in a way that one model will allow you to do predictions for thousands of other similar models. And to do that, we have to discuss what is called the exponential family of distributions. This is your homework set. I'm assuming you already have worked problem, what was it, 1 or 2? So you don't, all of this look very familiar to you. So let's define it. When it says family, right, it implies many, many distributions that fit under the same model. So if we manage to do inference in this general form, we have included many, many distributions. And the results basically transfer from a Gaussian to a beta to a gamma distribution, etc., to any distribution that fits in this category of what is called the exponential family of distributions. So what's the exponential family of distributions? Is the distributions that fit in this form that you see there, where these parameters theta are what they call the natural parameters of the distribution. By the way, you maybe forgot, but last Friday we were talking about an alternative way of writing Gaussian processes. You remember? I mean Gaussian distributions. The canonical form of Gaussian distributions. That actually, when you look at it, fits directly on this exponential family. Okay? So let's see what we have. We have some parameter theta, and a factorization that has an exponential, that's why it's an exponential family, of eta transpose, so obviously eta is a vector, times u of x, all right? This exponential will be what tells you if potentially you have an exponential distribution, times some function of theta, times some function of x, and you can rewrite this in a slightly different form by plugging in this g inside the exponential. And how do you do this? By defining this function of theta as minus log of g. All right, so you can put this inside minus log of g. Now, You can also write this, with the normalization factor explicitly given, as you see on the equation on the bottom, right? So you can have a normalization factor explicitly, and this normalization factor is basically 1 over G. I mean, you can see immediately if you integrate this distribution in X, right, you should get 1. So 1 over G is the normalization factor of this distribution. Okay? So, now, why are we studying the exponential family? We study because by spending some time talking about this, we're basically accounting for doing Bayesian inference for many, many, many different distributions. And whatever results you come up with for this distribution, you basically can transfer them to many other distributions that belong to this exponential family. So we want to study what are the properties of these exponential family distributions, and things will get a little bit tricky now. And I have to admit, even the lecture on Wednesday, I'm going to post a slide so you look at them, because we will come up with some results that may look a little bit complicated, but they're not. So, so let's do one example. And this is your homework, by the way, so I appreciate that you thank me. This is the Bernoulli distribution. So heads means x equal to 1, x equal to 0 is tails, and the probability of heads is mu. So what you see here on the top equation is the moment parameterization, right? Mu is the mean of the distribution. That's the moment parameterization. So we're asking, is this an exponential family distribution? Well, if you get trained to do these tricks, can I do this? Can I write this, the exponential of x log mu and 1 minus x log of 1 minus mu? Yeah? I mean, this is log of mu to the power x, this is log of 1 minus mu to 1 minus x, all right? And I have exponential, and if I get rid of the exponential of the logs, I get back to this, all right? So, yes, I can, and to put it on this form, right, this is our general class of distributions, I can keep my x log of mu divided by log of 1 minus mu, and then the log of 1 minus mu and x I can put outside as 1 minus mu. So there's my g of theta, all right? H of x equal to 1 here, and these are my parameters eta, which is this log of mu divided by 1 minus mu. Okay? So the Bernoulli distribution belongs to the exponential family of distributions. Now, I want, so I write basically all the generic symbols that we had here. I write them on the bottom to tell you explicitly what every term on H and G and U are. Okay? So I forgot to mention, and if I have time, I will justify it today. This U of x, you know what it is? What name should I give to U of x? We use it today in the beginning of the lecture. Look at the distribution, right? And there is eta transpose U of x. So what do you think U of x will come to be by miracle? The sufficient statistics for this distribution will be some function of the data that defines basically the parameters theta in that distribution. Okay? That's another major thing. Okay? But let me tell you another extremely major thing. Okay? So what we study up to now with this moment parameterization, it was written in terms of the moments like mean and variance, notice from here when you do this, the coefficient eta, these natural parameters, is the log of mu divided by 1 minus mu. So when you invert them, you can, first you notice that you can compute the moment as a function of theta. And this is a unique property of the exponential family. You can go from moments to eta in each direction you like, okay? And it comes out nice that the mean mu, it is basically a sigmoid function of theta. Now, you may say sigmoid function, what is that? Well, if for those who have taken any other course